Hi, I'm Dean, and I'll be presenting on quantum distributed algorithms for detection of cliques. Okay, so let's start with a 2-minute overview about what it is that we do. We tackle subgraph existence problems. In such problems, we have some large input graph. We're given a small subgraph, and we're asked to do one of 3 things with it. The first is to try to detect it. Does the subgraph exist anywhere in the input graph? The slightly more complicated version is to count how many instances of the subgraph exists in the input graph. And the final, most complicated version of these problems is listing. We want to give an actual list of all the instances of the subgraph in the input graph. In a distributed world, each of these problems also has its own definition. For example, for listing, every single computational unit in the cluster has to output some list of the instances of the subgraph that it sees, such that the union across all the computation units is exactly the list of all the subgraphs in the input graph. What we do here today, we show how to take an algorithm for listing all cliques of a certain size p, for any value p, in the distributed non-quantum setting, and convert it into an algorithm for detecting cliques of larger size in the quantum distributed setting. And we do this through a framework that we call nested grove research. This is the first time in the distributed quantum computation that grove searches were nested inside one another. All previous works only use a single grove search where the checking algorithm is classical and not quantum. Second, the way that we show the framework allows it to be used without any knowledge of quantum required. That is, any distributed researcher can take our framework and simply apply it as one more additional tool. Some examples for the results that we show. We take an algorithm for listing all triangles, that is cliques of size 3, in n to the 1/3 rounds in the non-quantum setting. And we show how to transform this algorithm into one which detects cliques of size 4 in the same round complexity. In general, the main result that we get is as follows. The blue line shows how long it takes to list a certain size clique in the non-quantum setting. And the red line shows how long it takes our algorithms to detect those same types of cliques. For example, for cliques of size 3 for triangles, listing requires n to the 1/3 rounds in the non-quantum setting, and detection in the quantum setting takes n to the 1/5 using our results. Same goes ahead for all the rest of the cliques of all sizes. We show faster results for any size clique. Surprisingly also, this difference is separation in the quantum setting, because the lower bound for listing actually holds and is the same as the blue line also in the quantum setting. That is, we show in the quantum distributed setting that detection of cliques can happen faster than listing. Such a separation is currently unknown in the non-quantum setting. Okay, so before we delve into the quantum stuff, we back up a little and we see what does subgraph existence look like in the distributed setting in the non-quantum setting. So we deal with a model called Congest. In the Congest model, we proceed in synchronous rounds, and in every single round, 2 neighboring nodes can send a log and bit message to one another. When we take this to the quantum setting, the only difference is that these bits can be qubits. The computational measure in this model is that we measure the number of rounds it takes for an algorithm to halt. The local computation is considered for free. A slight modification of the Congest model is the congested clique. In this model, it's exactly like the Congest. However, every 2 nodes can now communicate every single round, regardless of whether or not they're neighbors. So basically here we split the graph into 2 cases. We have the input graph, which is the input that the nodes get, and we're asked to solve problems over the input graph. But the nodes communicate using the overlay graph, where every single node can communicate with every other node every single round. Okay, so the problem of listing cliques was first tackled in the congested clique setting, where almost a decade ago it was shown how to list cliques of all sizes. It turned out that this result was optimal, and matching lower bounds were shown. Later on it was shown that it's possible to count triangles faster than to list them. However, it was also shown that it's difficult to show any lower bounds for this problem, practically any lower bounds, because otherwise it would imply lower bounds in circuit complexity. Later results went ahead and also showed algorithms which are sparsity aware, and they are tight. That means that even if the graph itself is sparse, the input graph, it's possible to list all cliques faster in those types of graphs. Leaving the congested clique aside, and the problem almost solved there completely, researchers turned their attention to Congest. What happens in the Congest model, which is way more restricted than congested clique? In this setting, it took a line of really beautiful works to get to an optimal result, which shows that listing all triangles in Congest takes n to the 1 over 3 rounds. And this is the same round complexity as Congested Clique, which is very surprising. It's one of the only problems currently known whose complexity in Congest and Congested Clique is identical. As for just detecting triangles, currently the best algorithm is still the listing algorithm and takes n to the 1 over 3 rounds. It's an open question whether this can be improved. The only thing that we know in terms of lower bounds is that we need more than one round in order to solve this problem. And recently, it was shown that showing any polynomial lower bound is difficult as it would imply bound and circuit complexity. And this area here that is still untouched is a very big open question in the distributed subgraph existence problems. Additional results for triangles include as well local listing, which is a variant on listing, and deterministic versions, since all the algorithms we just saw, almost all the algorithms we just saw, were randomized. And still in Congest, now the big question becomes what happens with cliques of larger sizes. What if we leave triangles aside and get into cliques of size 4, 5, 6, and so forth? Well, a lower bound still holds, and this was known for a long time. Recently, algorithms were shown that were sublinear in listing all cliques of all sizes, until an algorithm was shown that it was optimal and lists all cliques optimally in the Congest model, and it turns out this is the same round complexity as required in the Congested Clique model. Further, it's also known that for cliques of size 4, the time required to list or detect cliques of size 4 in Congest is exactly the same and sits at square root of n number of rounds. In the quantum distributed setting, some algorithms were given. However, it began already in 2014, where it was shown that for many problems, it's not possible to speed up using quantum computation. Recently, it was shown that it's possible to compute the exact diameter faster and even quadratically faster if the diameter is small. And it was also shown that detecting triangles in the quantum Congest model can be done faster than in the non-quantum Congest model, in the regular Congest model. As for the Congested Clique, there is only one result currently known, which is that exact APSP can be computed faster than what's known classically. Okay, so let's delve into what we do. We'll start with a warm-up. We'll take an algorithm for listing cliques of size p and extend it using just Grover search to an algorithm for detecting cliques of size p plus 1. Okay, and we'll do this in the Congested Clique. Recall that in the Congested Clique, every two nodes can communicate every single round log n bits to one another, and in the quantum Congested Clique, it's log n qubits. Okay, Grover search basically works like this. Say that we have a binary array, and we know that at least one of the entries is 1. It's possible in square root of n number of queries to find such an entry, or to say that no entry exists, and that is that the entire array is zeros. In a more general form, we have some function f, which gets input from some domain capital X, and gives us, and we desire to find some x star such that f gives it 1. If such an x star exists, then it's possible to do so in square root of the domain size. Recently, it was shown how to use Grover searches in the distributed setting. And basically the way that it's done in the distributed setting is as follows. The function f becomes a distributed algorithm. That means that we have some leader node, which coordinates the search and locally performs the search. And whenever we have some value x which we want to query the function f with, the leader node gets this value x, and then runs some algorithm using the entire network to compute the value f of x. And after some c number of rounds, the leader node should have f of x stored in it. This is an entirely distributed algorithm which computes this f of x. And then the leader can, using such a tool, the leader node can run the Grover search locally to find such an x star, and the number of rounds that it takes is the number of rounds it takes for a query of one result, which is c rounds, times square root of the size of the domain. This is distributed Grover search, an adaptation of the well-known Grover search to the distributed setting. Okay, so how does it work in our setting? We start with an algorithm for listing cliques of size p for some value p, for example 4. So we list all cliques of size 4, and that means that every single node in the graph outputs some list, and the union of all these lists is exactly all the cliques of size 4. For example, perhaps this purple node will output this orange clique. It doesn't have to be that the node outputting the clique is one of the nodes itself, in the clique itself. Okay, how can we check, given that we did this, how can we check if there's a clique of size 5? Well, how can we check if a certain node, for example, this node, participates in a clique of larger size? If we tell all its neighboring nodes to broadcast that they neighbor this green node, then every single node in the graph, which will know of a K4 that can be extended to a K5 using the green node, will be able to see this. For example, take this pink node here that already knows this cluster, this clique of size 4 surrounding the green node. Once these nodes broadcast that they neighbor the green node, then the pink node will be able to detect that such a clique of size 5 exists. Okay, so this basically is an algorithm for detecting if a single vertex can extend a given clique of size p to a clique of size p plus 1. And it takes us O of 1 rounds in the clique to check this for one vertex. So that means that if we check all the vertices using a Grover search within a square root n number of rounds, we can check if any vertex can extend some clique of size p that's already known to a clique of size p plus 1. This gives us that we can perform kp plus 1 detection in square root of n number of rounds, plus the round complexity that it takes for listing cliques in the classical setting. Okay, now let's try to bring it up one more notch. What if we nest the Grover searches, and instead of extending by 1, we extend the cliques by some t for some value t? Okay, so here's the algorithm. This is where we stopped previously. The classical step was to list all the cliques of size p. Then we had some classical checking algorithm to detect if we should extend the clique by 1 using some node. And we ran this using a Grover search. What if we change the quantum algorithm itself, the checking algorithm itself, and make it quantum instead of classical? Intuitively, what we get is nesting the Grover searches. We have some setup cost, which is some classical algorithm that we run, and then we perform some Grover search. And the checking function itself is also a Grover search, which nests other Grover searches. For example, let's see how we extend by 2. When we try to extend by 2, we have already listed all cliques of size p, and we want to check if there's a pair of nodes which can extend some known clique of size p to a clique of size p plus 2. The problem with, so the intuitive option is to just search over all pairs, and for each one to broadcast their neighbors and see if it can extend a clique to a larger size. The problem with this is that the search space is at least n squared. And so no matter how long it takes us to check a single pair, we'll take at least n rounds. To overcome this, we do the following. We take the search space and we partition it into parts such that we have square root of n parts called a1 to a squared root of n. And we search over these batches. So assume that the cost of searching over one batch is c, to see if this batch has some pair which extends a kp to kp plus 2. If we search over all batches in quantumly, it'll take n to the 1 over 4 rounds times c, since they're n to the 1 over 2 batches. Okay, so what's this value c? How long does it take to check if the single batch has a pair which extends a kp to kp plus 2? What we do here is we do the following. We start by broadcasting all the neighbors of AI. And this takes square root of n number of rounds, since that's the size of AI. What we do then, we search now over the nodes V to see if there is some node in V, which given some node in AI extends, both of these together extend some kp to kp plus 2. This is done exactly like we did the extension to p plus 1, simply by having the nodes in V broadcast their degrees throughout the quantum search. And this takes n to the 1 over 2 rounds because we have n nodes, and checking for a single node simply amounts to broadcasting its neighbors, and that's all, and that takes O of 1 rounds, as we saw a second ago. What this gives us is that checking if a certain batch has a pair that extends from kp to kp plus 2 takes square root of n number of rounds. So if we plug this value in instead of c, we get that the round complexity for checking if there are two nodes which can extend the kp to kp plus 2 takes n to the 3 over 4 rounds. But wait, why did this work? Why intuitively did we manage to go below n rounds for extending by 2 nodes? The reason being that when we broadcast the neighbors of AI, classically, and then we perform the quantum search, throughout the quantum search, this classical information is being reused. That is, we broadcast this information once classically, But throughout the quantum searches, every single node can still use this classical information because they possess it. Okay, so in general what we get here, we can extend this up to any value t. And what we get is that if we apply the known classical algorithm for listing cliques of size p, and add to it our addition, which extends by t rounds, we get the following runtime for detecting cliques of any size. And so, for example, if we want to detect cliques of size 5, we can run a K4 listing algorithm and then extend by 1. If we want to detect cliques of size 36, for example, it's optimal to run an algorithm for listing cliques of size 32 and then extend by 4. Okay, so we managed to show an algorithm which allows us to extend cliques. However, it turns out that it doesn't improve the runtime for cliques of size 3 and cliques of size 4. The reason being that even for just our +1 extension, we need to pay square root of n number of rounds. However, listing cliques of size 3 and of size 4 takes n to the 1/3 and n to the 1/2 rounds respectively already. So our extension doesn't help for these cases. And so it turns out that in order to solve this problem, what we need to do, so far we used a black box listing algorithm. We just used an existing algorithm somewhere in the congested clique, and we didn't use any of the properties specifically to a certain algorithm. We need to open up this box. We need to now tailor this listing algorithm to be able to work with the quantum algorithms that we show. And so let's start with an example of how we take K2 listing and show K3 detection out of it. Where K2 listing is basically just a redistribution of the edges in the graph, because K2 is just an edge. Okay, so we start by taking the set of nodes in the graph V and just arbitrarily partitioning it into n to the 1/5 parts, where each part is roughly of the same size. We create another partition, the green partition, into n to the 2/5 parts. It's the same partition, we just copied it here twice on the slide. 2 green partitions, which are the same, and the blue partition. Now, what we do is, for every single node u in the graph, we give it a triplet of parts. That is 2 parts from the green partition and a blue part. It turns out that there are exactly n ways to choose 3 parts in such a manner. And so every single node in the graph can choose one specific unique triplet of parts. Then what node u will do, it'll classically learn all the edges between its green parts. And since there are n to the 6/5 edges between these 2 parts, it's possible to do so in n to the 1/5 rounds. Classically, it's possible to show how this can be done. Now what we do, the node u will take its part in the blue partition and break it up into n to the 2/5 subparts, which also have n to the 2/5 nodes each. And notice now that the number of edges between every single one of the subparts and the green parts is at most n edges. And so it's possible to show in the congested clique that node u can learn these n edges in 1 round. And so basically what node u now has is the ability to check if any of these subparts can give a triangle in all of 1 rounds. And node u can run a quantum search over all its subparts and solve this and detect if there exists a triangle using with a node in every single one of its parts in n to the 1/5 rounds. All nodes in the graph do this in parallel for their triplets, and so what we get that in n to the 1/5 rounds, all the nodes in the graph can check if there exists a triangle in the graph. In general, we can extend this to any p and not just K3 detection, based off by taking the listing algorithm from 2012 and augmenting it directly with our quantum searches. And we can also extend it to plus t and not just +1. That is, we can add any number of nodes that we want to. And what we end up getting is the following formula for KP detection, where if we want to detect cliques of a certain size, we should minimize on what size clique Q we want to list, and then extend that by t more to get to p. Okay, so far we just talked about the quantum congested clique. How about quantum congest? What happens there in the much weaker model? So in the congest model, recall that every 2 nodes can send a message to one another, whereby in the congested clique, every 2 nodes can send a message to one another, and in the congest, every neighboring nodes can send a message to one another. This is what we did a second ago for detecting triangles in the quantum congested clique. In order to turn this into a quantum congest algorithm, we need to do 2 things. The first is we need to randomize these partitions. They can't be arbitrary. And this is to help out with load balancing problems which occur in congested and not congested clique. And the second, we have to attach this to a framework which was shown for listing triangles in the congest setting. And we combine the framework with what we showed here in order to get the algorithm in congest. Finally, we also show how to extend cliques of any given size listing to detection of +1 of that. And the way we did this in the congested clique setting was that we searched over all the nodes, and for every single node, we broadcast the node of 1 rounds its neighbors. However, in the congest setting, this can be very, very challenging to do. And so what we end up having to do, we take the framework which was recently shown for listing cliques of any size in the congest setting, and we augment that. What this framework gives us is that, one, we only have to consider nodes with very high degree, where the degree is at least the average degree in the congest model, and it's also at least n to the 2/3 round nodes. And we're also given that messages can be sent very quickly in this setting, basically meaning that even though we're in congest, any 2 nodes can communicate messages to one another, as long as no node sends more than O of its degree number of messages per round. And so given these constraints that the framework allows us to assume instead of just working in the normal congest model, we now bucket the nodes in the graph according to their degrees, and we go over each of the log n buckets. In each bucket, we search over the nodes in that bucket to see if one of them can extend a known clique of size p to p+1. Working out the math shows that it's possible to search over each bucket and enter the 2/3 rounds. Since we have log n buckets, it takes O tilde, which is log n times enter the 2/3 rounds in order to search if there's any node in the graph which extends a kp to kp+1. Finally, also in congest, we show hardness of proving lower bounds. It was shown previously that for cycles, it's difficult to show lower bounds for cycles, either because it's impossible using 2-player communication complexity, or because showing lower bounds would imply lower bounds for circuit complexity. It was also shown that for triangles, it's really difficult to show any lower bound, any polynomial lower bound for detection of triangles. We go ahead and we extend this, and we show that for cliques of any size, it's difficult to show lower bounds higher than n to the 3/5, polynomially higher than n to the 3/5. And we do this by combining the lower bound for triangles with the framework which was recently shown and some additional observations that we have. Okay, so to summarize everything that we've been through, we start in the quantum congested clique, and we show how to extend clique listing of size p to clique detection of size p+1 by searching over the nodes in the graph. If we want to, we later show how to extend using nested Grover searches by t and not just by 1. We also then open up the listing algorithm itself and adapt it to be able to use specifically with our quantum searches. This also allows detection triangles in K4 faster. Also, it shows a faster result for general cliques. In quantum congest, we go ahead and we take our K3 detection algorithm from the clique, and we add sparsity awareness to it by having this randomization and some load balancing techniques. And in order for cliques of larger sizes, we have to use the frameworks which were recently introduced. Finally, also in congest and in quantum congest, we show hardness of showing lower bounds for detecting cliques of any size. And this is based on combining the recent lower hardness which was shown for triangles with the framework which was recently shown and some of our additional observations. Thanks so much for listening. This is it for today.